Let's take a look at practice quiz number 2 here, everyone. Physical quantity, question number 1. The physical quantity that can have the same unit as impulse would be, this is, we talked about category 1, category 2, category 3. This is a definite category 1. We have to get this question, right? Now, if on a practice quiz you make a mistake on this, whatever, right? Who cares? It just tells us that we need to learn something so that we can get this question on a test or on an exam. What is the answer to question number 1? What has the same units as impulse? Yeah, it's going to be momentum, right? Because the way we define impulse is the change in momentum. A change in momentum is going to have the same units as momentum. 2, a rock climber falls and is saved from injuries by a climbing rope that is slightly elastic. The importance of the elasticity of the climbing rope can be understood in terms of impulse because elasticity results in what? What does, forget about the physics for a second, just kind of every day, what does the climbing rope do, the elastic climbing rope? It cushions an impact, right? We can fall and we can hit the ground, or we can fall and the rope can stop us, or we can fall and some non-elastic rope can stop us. What does the elastic rope do? We knew we were going to get this question on a practice quiz. We know we're going to get it on a real quiz. We know we're going to get it on your unit test, right? It just might not be a climbing rope. It might be an airbag, or it might be a bending the knees, or whatever. What is it? Okay, so if it stretches, what does that do? Like, what's the physics purpose of that rope stretching? Yep. Yes, the impulse is going to be the same whether it's a rope that doesn't stretch or whether it's a rope that does stretch. The impulse is going to be the same. We increase the stopping time, and when we increase the stopping time, we decrease the force. So that's A. I'd put that as a category 1 question too. Although we do have to, it's not straight recall. We do have to understand that a little bit. So maybe a 1B, but it's still a category 1. We definitely want to get that. Okay, we got some information here about a skier leaving the gate. I've told you before, when we see this information, we're going to skim it. But we know that the majority of it's probably not going to be relevant. I think that always happens. Okay, sometimes we get way more information than this. Sometimes we get an entire page of information. Most of it's not relevant. But we do want to skim through it. Not necessarily read it in detail. Skim through it, and then when you then read the question and then go back to the information and find what you're looking for, okay? Read through it in a little bit more detail once we know exactly what we're looking for. So this talks about the starting gate. We're leaving the starting gate, and then we go down the hill, and so on and so on and so on. I'm not going to read through it with you. I'm going to assume that you've read it already when you did your homework. But again, I'm not asking you to read it in detail the first time. I'm asking you to skim it the first time. Go back and look at the details of it once you know what the question is. Number 3 says the magnitude of the impulse on the skier as he leaves the starting gate. So the relevant section of this is leaving the starting gate. That's this, right? This is the relevant part of this question, right? As he leaves the starting gate. If we're looking for impulse, we know we're going to say delta P is equal to either F times T or M times delta V. Which equation are we going to use for impulse? M times delta V. Good. M times delta V. F times delta T is absolutely valid, but I don't think it would be very helpful to us here. You can try it. It's not going to get you an answer. Certainly go to the other equation, right? My mass here, I don't see it in that first paragraph. I do see it down here, 68.2 kilograms. And then we say delta V is VF minus VI. What's VF? Yep. Yeah. Part of the reason that I gave you this particular question was to point out to you sometimes the wording of a question can trick us. It says here the skier leaves the starting gate with an initial speed of 1.6 meters per second. But we're not making that our initial speed. We're making that our final speed, or final velocity. Right? This is the initial speed if we're analyzing the trip down the hill. But that's our final speed if we're analyzing the starting gate. Does that make sense to you guys? But just because they use the term initial doesn't mean that for us it will be the initial. It's not like they're lying to us, right? They're just describing this term, this 1.6 meters per second, in terms of the second phase of this, right? The trip down the hill. Now, the initial speed would be what? 0. Yeah, you're 0 when you're standing in the starting gate. That's right. Now, be careful here, right? We get caught up sometimes in just seeing numbers and not necessarily like looking at the context of those numbers. I see two numbers here, 20 meters per second, 33 meters per second. There's a risk of picking those two numbers out and then saying delta V is 33 minus 20. Well, if you're trying to find some other impulse, it could be 33 minus 20, but it's not. That wouldn't be the impulse as the skier leaves the starting gate. Does that make sense, you guys? So let's follow the strategy of skimming the information box, reading the question, and then going back and finding the details. But know what you're finding the details for. We're finding the details specifically, and we have to be very deliberate about this. We have to notice this specifically for as the person leaves the starting gate, not just random speeds or velocities, but as he leaves the starting gate. We do that, not so bad of a question, right? I'm going to make this a category 2 question. Mathematically, it's a cinch, right? Easy. Mathematically, once you get the right numbers into the equation. But getting the right numbers into the equation is what makes this a category 2. Not crazy hard, but not a category 1 either. What does that work out to be? 68.2 times 1.6. 1.09 times 10 to the 2. Okay? Good. Oh, wow. Talk about a page of information. Holy, I forgot that this one was there. I'm not going to read through that, but let's pretend we're skimming through it right now. We're just going to pretend that we're skimming through it right now because presumably you guys all read through it last night when you were doing this for homework, right? It talks about these permanent magnets and propelling this car or this this car and so on. It's got these electromagnets. We don't even know anything about a lot of that stuff. We will learn about magnets later on this year. But the point that I want to make with this one, looking for impulse. I want to show you how to calculate impulse. But probably bigger than that in this question is to show you that, again, strategically, we skim the information, but we don't worry about most of it because most of it will be irrelevant, right? Let's look at the question, pretending we've skimmed it already. The magnitude of the impulse that the car experiences as it accelerates from position 2 to position 3. So look, we're only looking at this stuff. That's it. The impulse right here from position 2 to position 3. Why are we going to waste time on focusing on details of the rest of this, right? If the context of this is interesting to you, we'll go back and read it later. But during a quiz or a test, we're not going to try to learn about these cars. We're just going to try to answer the question. That makes sense, you guys? And if it's actually interesting, which maybe some of this stuff is, then you can go back and read it later and actually learn about it, if you are so inclined to do that. Okay, we're looking for the impulse of the car experience as it accelerates from position 2 to position 3. I'm going to say m times delta p. The mass I do need from somewhere else. I got to find the mass somewhere. 5.44 times 10 to the 3. Notice I'm not looking for all kinds of stuff in this information. I'm looking specifically for mass because I know that's what I need that's not down there in the picture. So I found it. I'm going to say 5.44 times 10 to the 3 kilograms times VF minus VI. And VF and VI are both here. 4 minus 1.5 is 2.5 kilometers per hour. We're going to convert that to meters per second. 0.6944. That makes sense what I just did there, guys? Now, be careful. What I just did is absolutely fine. Subtract them as kilometers per hour and then convert the delta V to meters per second. How many people converted both of those to meters per second and then subtracted? That is also absolutely fine. Okay? You can do it either way. If this bothers you, what I just did, then just convert them both. No big deal, right? It means an extra 5 seconds of conversion. Okay, let's multiply these together and see what we get here. 5.44 times 10 to the 3. 3.78 times 10 to the 3 kilograms meters per second. The answer is D. Definitely a category 2. Okay? Very doable question, but it's not a gimme question by any stretch of the imagination. Good there? Question 5. Is it just 5? I thought there was 6 on it. Oh, yeah. Foundation piles for tall buildings are hammered into the ground using pile driver. Pile driver is similar to the one shown below with a 900 kilogram hammer, distance of 3.5 meters above the top of the pile, and then it's allowed to drop. So we drop the hammer 3.5 meters, the hammer falls, and then it hits the pile. And the hammer's going to stop, right, after it hits the pile. What's the magnitude of the impulse delivered by the hammer to the pile? Now, we're going to say delta P is equal to M times delta V for this. M is 900 kilograms. You ever seen this? You have. You absolutely have. You know what the point of this is? Like when they're building a big bridge or an overpass, right? When they were building Stony Trail there around, like all the crazy overpasses. And even now, when they're, you got Deerfoot, like construction everywhere on Deerfoot, right? You get up to Anderson Trail, and they're doing this crazy interchange there because it was always like a traffic bottleneck there. When they start these projects, they always hammer these piles into the ground. They do this for tall buildings as well. Sometimes we call these piles friction piles. You know what the purpose of them is?
No, but when I looked at this photo, I thought.
Okay. Okay, fair enough. We're not actually drilling there. We're literally just hammering these piles into the ground. Friction piles, sometimes they're called. What happens is these piles get hammered into the ground just a little bit at a time, right? We raise this hammer, we drop the hammer, bang. Raise it again, bang, and it goes in just a little bit every single time. And the further it goes in, the more soil it displaces. And the more soil it displaces, the more force pushes back on the friction pile, right? The more you hammer it in, the more friction acts between the pile and the ground, between the pile and the earth. If you have one of these hammered in there, like all the way down or a long ways down, there's going to be a tremendous amount of friction between the earth and this friction pile. You put another one in, double it. Put another one in, you've tripled it, right? So what's the big deal there? Well, listen, if we build something like a bridge or an overpass or a building, like we need to have a solid foundation, right? The wise man built his house upon the rock, right? Now, if there's no rock, the wise man built his house upon foundation piles because that provides the foundation, right? You put a heavy building on top of this, and if there's enough friction, then it prevents the building from sinking. Literally, friction will prevent this building or this bridge from sinking into the ground. Just friction. That's it. Yep. And it's still on top of it, yep. And it's crazy, right? Like to think they built a city that way. And that's, and you talked about like, well, in 2024, we drive these piles down and it's like, well, we've been doing that for a long, long time, right? Yeah, absolutely. Except normally we don't use wooden piles now, but I think if I remember reading that those are still actually have survived really well. I forget what the reason why they survive so well. Maybe it's a lack of oxygen in the water or something. I'm not sure exactly, but I don't know. Anyways, mass is 900 kilograms. Delta V, what is VF? What is VF here? It is 0, yes. The magnitude of the impulse delivered by the hammer to the pile. Like once the hammer hits the pile, it stopped. So the final velocity is 0. Now, I saw somebody go like this when I said, what's the final velocity? Really, the answer to the question, what is the initial velocity is, right? We don't know what the initial velocity is. What's the velocity of this when it hits the pile? We're going to say, do a little VF squared is equal to VI squared plus 2AD for that one. Interesting, it's a little bit confusing with the VFs and the VIs here, right? We're actually going to solve for VF. VF is the square root of VI would be 0 squared. This is analyzing the fall, right? Not the collision with the pile, but this is the fall of the hammer. 3.5, yeah. Anybody get a value for this, for VF, of the fall of the hammer? Somebody must have this number. Yeah, just bear with me for a second here. Yep. 8.2867 meters per second. So this is the final velocity, final speed, I should say, the final speed of the hammer when it falls, right? During the fall. Make sense? When you drop the hammer, at the end of the drop, it's moving at 8.28 meters per second. But that becomes the initial velocity for the collision with the pile, right? It falls, and at the end of the fall, it's moving at 8.2, and then it hits the pile. So it's moving at 8.2 when it first hits the pile. So we're going to say the initial velocity is, the final velocity for the fall is 8.2. The initial velocity for the collision with the pile is 8.2. Because it's not really 8.2, it's negative 8.2. Because the speed was 8.2. The velocity is negative 8.2. 0 minus negative 8.2 is just 8.2. We multiply those together. I think it was 7.46 times 10 to the 3, which is 7.46 kilonewtons seconds. Now, you probably could have gotten away with making this, the final velocity, or because the other one was 0, right? In both cases, the fall and the collision, the other velocity was 0. You probably could have gotten away with mixing up the initials and the finals. But technically, that's what we're doing, right? You understand the difference between the initials and the finals there? Okay. And number 6, I think number 6, they just ask you for the force, isn't it? Yeah, we're looking for the force there. So we're going to say delta P is equal to F times delta T. And we're going to say F is equal to delta P over delta T. We really should have the unrounded number here, 7.46 times 10 to the 3, but I don't know what that is. And I think we're going to get away with it here. The time here is 2.1 times 10 to the negative 3 seconds. Divide those two. Once I get a calculator going here, here we are, 7460 divided by 2.1 times 10 to the 3. 3.55. 3.55 times 10 to the what? No, something's wrong with that. What is it? Oh, it's negative 3. Yeah, you're right. Yeah. Yeah. See, look, I just made a mistake, right? But I caught that mistake. There's no way it's a force of 3.55 newtons when this hammer hits the pile, right? Just doesn't make sense. Making a mistake is okay. But if we just stop and see if our answer is reasonable. So we're going to go times 10 to the negative 3. 3.55 times 10 to the 6, yeah. Although, this is the first time we've had to do this, express a numeric response here. When we have a b times 10 to the w, we're just looking for the value of b. That's the base of this number. So we would just express 3.55 here. Some people will express a 4 there because they'll say, oh, B's got to be a 1-digit answer, right? B times 10 to the W. What's B? No, no. B can be a 3-digit answer. This is B times 10 to the W. We're looking for the value of B, 3.55. Make sense, you guys?